groups with lots of p-local subgroups of characteristic P. So, as Ellen suggested, I'm going to talk about this project by Meierfrankenfeld, Stellmacher, and Stroth, and some contributions I've made to it. I'm going to start off just as Ellen did, because I've not seen Ellen's talk. I started, but anyway, we can repeat some things and perhaps highlight some points. So, the finite simple groups, then, just as Ellen mentioned, we have this bulk of them in the middle that are the finite simple groups of Lie type in characteristic P. Right, so this talk is about fixing a prime P and trying to classify or determine the groups that are very much like the Lie type groups in characteristic P. So it's not like Ellen was talking about where she fixed, say, a prime 7 and was looking at an involution 2, a prime 2, and then taking that centralizer where things are somehow in the cross-characteristic case. Here I'm going to be in the characteristic P case. And what's going to happen is that we're going to see that as we go through some of the steps, the sporadic simple groups drop out as well, as being examples of groups that are like Lie type groups in characteristic P, but actually are not. They're sporadic in and don't fit into the general picture, but they pop out in the investigation. Yeah. The alternating groups don't pop out so much. All right, so just like Ellen said, you can edit your slides while somebody's talking. Lie type groups stand out as being the most typical type of finite simple group. And again, like Ellen mentioned, here's the definition of a p-local subgroup. So I've got a non-trivial p subgroup T of G, and a p-local subgroup, by definition, is just the normalizer of that subgroup. So you're going to have lots of p-local subgroups, but you can always conjugate T into your favorite C-low P subgroup. Yeah, so this is where the fusion system approach starts appearing. You've got your fixed post, which is your fixed C-low P subgroup, and you move T inside it. Yeah, so you have your p-local subgroups. And again, this is just as Ellen pointed out. We have this condition here. You take a p-local subgroup. Right, so the nice thing about p-local subgroup is that it has a normal subgroup of order divisible by p, by definition. It's a normalizer of a p subgroup. You take the biggest normal p subgroup in there. That's the OP. So here is your OP of H. So H is the p-local. You've got OP of H. And one of two things happens. Either the centralizer in H of OP of H is in OP of H. In other words, it's the center of OP of H, or it's not. Yeah? And so we have this condition. And this happens for every p-local subgroup in a group of Lie type defined in characteristic P. That's the Borel-Titz theorem. Right, so it's got to be a simple group, obviously. If we have the center sitting there, so if I was looking at SL and not PSL, the center of SL, given that N and P minus 1 or Q minus 1 are not coprime, will be sitting inside that centralizer. But so this is our property that we isolate as one that seems to be a giveaway property for being a group of Lie type in characteristic P. Yeah? And so we just say a p-local subgroup H has characteristic P if and only if it satisfies this condition that is like the condition satisfied by a group of Lie type in characteristic P. And so, just as Ellen did, let's just draw some p-local or some maximal p-local subgroups in. And there'll be some decorations on top. So this is meant to be a picture of a p-local subgroup in SL, or GL, I don't really mind where you want it. And then we take the quotient to get you to the center. So what do you see? You've got this big normal P subgroup sitting down here, and this SL2 sitting down at the bottom here, for instance, will be a group of order q to the 4, that this SL2Q acts on here and on here, making a tensor module. Yeah? And so this condition here is trying to say OP of H is big, because these SL2s are not allowed to centralize this P subgroup here. So they've got to get modules in there for this group, for this SL2 cross SL2, and so it becomes big. So you should think of this as saying OP of H is big. Yeah, that's a rule of thumb. If we went to a saturated fusion system, then, for instance, if T was fully normalized, then NF of T is saturated, and we can just make the same definition for characteristic P. Yeah? So that makes sense for fusion systems as well. As mentioned by Ellen, we have this notion of local characteristic P. This is the same as what she called characteristic P type. All P local subgroups have a big normal P subgroup. Yeah? And then we have a weaker notion, parabolic characteristic P, which just says all the P local subgroups that contain S, that contain a CLO P subgroup, have characteristic P. Now notice that if you're in this case here, we have a CLO P subgroup contained in the normalizer, then surely that P subgroup is fully normalized. Yeah, because you can't have a bigger normalizer, P normalized, than the full CLO P subgroup. And so I would be for the fusion system case, that would say NF of T was characteristic P for all T normal in S. Yeah. I want to just say as well that if, let me take another P local subgroup inside SLN. I'll put lambda and lambda inverse, I don't know. So something like GL n minus 2 of Q. And then you have a big P group down here. Zeros up here. Okay, there's a P local subgroup. Here is the center of the CLO P subgroup. So normalizing the center, I can still have OP much bigger and become a characteristic P. Yeah? So even though the P subgroup I'm normalizing is small, the OP of the normalizer is big. Yeah? So it's just so that you get an idea of what's happening. So again, local characteristic P or characteristic P means big normalizers. Contained in an S. Yeah, you can't do anything about that. I could go and edit it if you like. Yeah. So it's stayed proper in S. I don't even know why I wanted it proper in. Yeah. So just have a look at a couple of examples and illustrate what I mean. So if we take the symmetric group of degree 8, which is isomorphic to SL42 with its field automorphism on top. Diagram automorphism, yes. Yeah, inverse transpose. Yeah. Then it's centralized. It's easier to think of it as symmetric 8. The centralizer of the transposition is then just 2 cross S6. Yeah. And we see that the O2 is very small. Yeah, that's this smallness again. Yeah, and in fact, these sorts of centralizers are precisely the thing that Aschbacher tries to rule out, not allow into his program, because he doesn't want to classify non-simple groups. So he insists that the involution is in a maximal rank abelian subgroup. I think that's right, yeah. And so these ones don't appear in his classification. On the other hand, if I take SL42, then we look much more like this, and everything is of characteristic P. And again, just like Ellen said, if I go back into L8Q, PSL8Q, Q odd, take this diagonal involution, then it's got this normal subgroup SL2Q, put the derived group on there just to deal with the SL23 case, central product SL6Q. It does not have local characteristic 2. And you see that the O2 here is just of order 2 if Q is bigger than 3, and otherwise it's just a Q8. So small O2s, not characteristic 2 type, small O2. Good. So I've got to do something a bit messy now. So for a P local subgroup L, G, which has characteristic P, YL is the maximal so-called P-reduced normal elementary abelian subgroup of L. P-reduced means that when I take L, I take the centralizer of this subgroup YL, factor out the centralizer, take the OP, I get a trivial group. Yeah. And so if I think very shortly, I see that YL is in omega 1, the center of OP of L. Because if not, then OP of L is not in the centralizer in L of YL. And so this is a normal P subgroup of the quotient. And that means that, so just running it across, means OP of L centralizes YL. So I get YL is in omega 1, the center of OP of L. And from now on, let's just think that YL is the center of OP of L. So in my picture here, so when I take this P group here, this OP, YL is just this tiny Q to the 4 at the bottom. Yeah? And then all the rest of this group, we don't know. This is the center. And it's just a tensor product module for this SL2Q cross SL2Q. In this case, YL is just the center here. Yeah? Doesn't get any bigger than that. This is a group that has derived subgroup, just this root group here. And yeah, that's it. That's YL in that case. And if I took a different parabolic subgroup, so you can get YLs to be very big. So if I take then the YL group is this whole thing up here. Good. I've got 3 different YLs there. And in all those instances, YL is the center of OP of L. Right, so here comes a horrible group to meet any day of the week. Yeah, so suppose the test is a CeLO P subgroup of G, and G is a parabolic characteristic P. So all the overgroups of the CeLO P subgroup now have this nice big OPs, chunky OPs. So it looks just like this group. Yeah. C is the maximal P local subgroup containing the normalizer in G of omega 1, the center of S. And we define E to be O upper P of FP star of the centralizer in C of YC. What a mouthful, eh? We're not going to have to deal with it for long. So here's the centralizer of the center of S. And in this instance, we take C a maximal P local containing this and looking at something like this, or its friend by the graph automorphism. Yeah, the one with the stars down the bottom. Yeah, and then YC is the all of that. Sorry, YE is all of that. And the FP star, what does FP star mean? I factor out OP of the centralizer in C of YC. So I factor that lot away. Yeah. Then I take the generalized fitting subgroup, which is the OP prime, sorry, yeah, the product of all the OPs for P, ORs for R not equal to P together with the components. Yeah, and look at that centralizer. And so here's one of 3 things that happen, which which forces the future investigations. it could be that C is the unique maximal p-local subgroup of G containing S. So there's just one maximal p-local. So whenever I take the normalizer of a p subgroup that's normal in S, it's trapped in C. Yeah, that's one case. The case we're going to look at, is that C is the unique maximal p-local subgroup of G containing E. Yeah, so that's not this case, but it's going to disappear in a moment anyway. But S is contained in more than one maximal p-local. Yeah. And then the other case is that E is in at least two maximal p-locals. Now, this case, I'm not going to say anything about. This case has been looked at by Meierfrankenfeld and Stellmacher using so-called pushing up arguments. And we're going to be interested in this case. So C is the unique maximal p-local subgroup of G containing E. So what does that lead to? Well, so in that case, assume that C is the unique maximal p-local subgroup that contains this E, whatever that E means. Set Q equal OP of C, then NG of A is contained in NG of Q, which equals C for all A contained in the center of Q. So this is a statement I want. Right, so what's it saying? It's saying take a subgroup of this thing here. This has typically got order Q, so there'll be lots of P subgroups in there. If Q is P to the A. Now, the normalizer for any P subgroup in here is contained in the unique maximal. So it's not the case here because there are two maximals. But it's surveying the subgroups of this YC, saying, look at where the normalizers are. So it's an embedding property of the normalizer of Q. Yeah. As the proof, we can show that YC is omega 1, the center of Q. So E centralizes YC. And then, obviously, omega 1 of A for any A subgroup of the center of Q is in omega 1 center of Q, so it's centralized by E. And so the normalizer of omega 1 of A is trapped in NGQ by the definition of there just being one overgroup of E. So E has a unique maximal overgroup. These P locals all contain E. So we've got these P locals are a unique thing. Good. All right, so now we can forget E for a moment, or forever. Yeah. Really what I wanted to get to was this. So you start with a group G, and you suppose it's got a subgroup Q, a P subgroup Q, that has the property that Q is OP of its normalizer. Yeah. So Q could be this here. Yeah. So if I take its normalizer and take its OP, I still get the same group I started with. And whenever A is a subgroup of the center of Q, the normalizer in G of A is in the normalizer in G of Q. So you can't escape from the normalizer of Q by looking at elements in the subgroups in the center. Yeah, so that's embedding this thing in some way, but not as strongly as strong P embedder. Yeah, so that's a large subgroup. We've shown that in case 2, the one we're interested in, Q equals OP of C is a large subgroup. So now we're going to forget this E group altogether and just look at groups G that have a large subgroup. Yeah, and forget about the complications, just look at this group with a large subgroup. So obviously the center of S centralizes Q, yeah. And so the center of S is in the centralizer in Q of Q, which is the center of Q. So we have that the normalizer in G of the center of S is in the normalizer in G of Q. So again, it's just very much like this picture. Yeah. But we got some arbitrary group G. You know, we got S, which we know nothing about. We got this subgroup Q. Yeah. And we know nothing about the structure of Q. We know nothing about the structure of NG of Q mod Q. Yeah. But I am assuming that there's some other maximal P locals around that we're not in case 1. Yeah. We're not in case 1. So there is some other P local subgroup around. So we don't know what the other P locals look like, but here's one that's not in NG of Q. So there is something else around. And what the objective is to do is to show that we're in from this group G that's just some mysterious group. It begins to look like GLN or SP or SP2NQ for some Q odd, or to some E8 of Q for various Qs. So so our objective is to get to the group structure of the simple groups without knowing anything about the structure to begin with. Oops. Seen that already, seen that. And the first thing that you prove, it's not so hard, is that if you have a large subgroup, then you already of parabolic characteristic P. So this one subgroup Q tells you that the normalizer of every overgroup of P, of S, every P local overgroup of S, has characteristic P. This one subgroup makes all the things look like a group of P-type already. If you survey the simple groups of Lie-type in characteristic P, all but these 3 families have a large subgroup. So if you can classify groups with a large P subgroup, you will see all the groups of Lie-type in characteristic P other than these 3 families. Yeah? And so that's our job. So we want to recognize SLN, SP when P is odd, symplectic groups over fields of odd characteristic. We want to recognize F4 of 5 to the n. We want to, and so on. So how do you do this sort of thing, and why can you do it now and not a long time ago? I guess that's the why didn't they take this approach 30 years ago, 40 years ago maybe? Well, one thing is something called the amalgam method. So this is a method in local group theory that exploits a graph that you can make from your P local subgroups. Now, so how do you do that? You've got this subgroup, say, and the one above, one of the ones above. You take the cosets of those subgroups in G, and you join 2 cosets if and only if they intersect. So you never join 2 cosets of the same type, obviously, because they don't intersect. Intersect non-emptily. And so it gives you a graph. And what the amalgam method allows you to do is keep track of taking normal closures of things. So for instance, let's start with this group here. Here's my little Y, group Y, or the center of S. When I view it over here, it looks like this little square corner. And so I take its normal closure in this subgroup, and it builds up this group here. And then I take this group back down here. And it's already, we see, messing things up. And the amalgam method allows us to keep track of these normal closures. So it's a notational device that helps you understand how things are working. Right, so that's one thing that we know. And the other thing that we now know about a classification of small modules with nice actions of P subgroups, the quasi-simple groups. And so I've got to define nice. Nice. So here's nice. Suppose G is a quasi-simple group, B is a faithful GFPG module, and A is a subgroup of G. It's a non-trivial elementary abelian P subgroup. Yeah. So quadratic pairs are interesting. So these are pairs where V has the property that when I take A and I take the commutator twice with it, so that would be like taking elements V A minus 1 squared, taking the span of those such things. I get 0. Yeah. Well then, a nice set of results of Schermak. So it shows that if P is odd, then you're looking at a group of Lie type and characteristic P. Or P equals 3, order of A equals 3, and you're looking at something like the Suzuki group per Conway 1. Yep. I think there might be another example. If P equals 2, this automatically happens because this is because A minus 1 squared is 0 for when P equals 2. Okay? And the other things that are interesting for us are things called F modules. You can see there's a development in our understanding of F modules as well over the last years. And so what this gives you are the triples GVA that satisfy this strange inequality and this strange inequality. Yeah. And so why is that interesting for me? It tells me that if I can spot this sort of information, I can start to tell you what things like this are. So let's look at this case here. I've got SL2Q cross SL2Q. Here is my Y group for this. It's an elementary abelian subgroup. So it's a module for SL2Q cross SL2Q. And then I find that some subgroup of this, say this one, which is elementary abelian, it acts quadratically. And so I begin to see quadratic action, failure of factorization actions, and it allows me to say something about the structure of this and this module here. Okay. So there's a problem. Right? So when they say these results actually use the classification, right? They say, suppose I'm looking at a group of Lie type, or suppose I've got a sporadic simple group, and I've got a module of this type, then this happens. And I want to be able to use that. And so I have to do something to make sure I can use it. And the right thing to do is to assume that you're in a minimal counterexample to the classification. Yeah? So a minimal counterexample to the classification then will be a group which has every composition factor of every proper subgroup, a known simple group. And we can be a little more careful about it because we're only going to want it in P local subgroups. We don't need to know it everywhere. We're only going to be looking at P local subgroups. Yeah? A group which, so we call such things a K group. Good. Go back to fusion systems for a moment. So in the fusion system world, we've got NF of T, say T is normal in S, so it's fully normalized. NF of T is a saturated fusion system. It's got characteristic P. That means T is what is called F-centric. And then there's something called the model theorem. I think it's 4.11 in AKO or something. Model theorem. It says there exists a group G such that the fusion system of G on S is the same as the fusion system NFT. So I can replace NFT, the fusion system, by a group G, and I find myself in very much the situation that I'm in, just analyzing the finite groups. Yeah? So as long as I don't leave my P local subgroup, I'm in good shape. All the P local subgroups glue together, but as long as I stay in them, the fusion system argument and the group argument will be the same. Yeah. So we've got a group G then, KP group if every P local subgroup of G is a K group. So this is the first main theorem in the MSS project. Came out a couple of years, 4 years ago now. What does it tell you? You start off with a group G. Well, here's the statement of the theorem. It says, then mostly the possibilities for this pair are known. Right? Let me try and explain what that really means. Yeah. So I have a picture. There we are, a local structure theorem. So what's it telling you? Starting off with some group G, it's a total mystery to us. Yeah. We've assumed that we've got some P local subgroup that is not inside the normalizer of Q. We've got the normalizer of Q, which is my group here. Yep. Although I don't know Q, yeah, and I don't know what the structure is on top, but I know I've got some subgroup outside. Yeah, and there it is. I know there's a YM. It can't be in YQ, which I'm assuming here is the center of S. Yeah. So here's the center. Here's my YM. Yeah. And what they're telling you is the structure of this module here for this quotient group here. Yeah. So they're telling you SL2Q cross SL2Q acting on this module, but nothing about the rest of the group at all. Yeah? It takes some 100 pages, some 200 or so, and 70 pages. Yeah, and so that's using the amalgam method and this property of 2F modules, F modules, and quadratic action. Yeah? And so this has been told to us for any M that they choose outside. So if they'd have chosen SL3 and SLn minus 3, it would have told the YM would then be this 3 by n minus 3 block. They'd have told you the structure of this and of this piece that's acting, but they wouldn't have told us that this piece was the whole of the OP. Yeah, so there'd be some mysterious part in the middle here that we don't know. Yeah. And on the other side, we have no idea what NGQ is. Yeah, good. That's clear. so it's but it's beginning to approximate what the finite simple group looks like. Yeah. Things that can come up are that we don't want are Reith products. So you can have things that are actually trying to be Reith products of simple groups, and they've got to be ruled out later. Good. So we want to go further. So LG of S is just a collection of P local subgroups that contain S and have non-trivial OP. So these are the P local overgroups of S. So here's another one of those nice case divisions where everybody can agree it's right. So case 1 is there exists a P local subgroup M such that M is not in NGQ and YM is not in Q. Yep. So this would be one of those. Look, here's this Q to the 4 and it's visibly not in this OP because it sits like that. Yeah. Or we could have for all P local subgroups M that contain S and M is not in NGQ, we could have YM is in Q. That's plainly two different cases. Yep. And then case 2, you can look at this normal closure and it's either abelian or it's not. And so there's 3 cases, 3 distinct cases. This and this are the real world. Here, there are, this bottom case here, there are a tiny number of examples. Say the Thomson group at P equals 3 is an example where you have this. But almost never does that occur. And Meierfrankenfeld and Stellmacher and Stroth have a preprint called the theorem, the small world theorem, because these are somehow small. When you're in this case, then this gap has to be very big. Yeah? Because you're taking these closures, you go YM closed over here, and you close it over here, and you close it over here, and you close it over here. This is this amalgam method. You're taking these successive closures of subgroups, one side and the other. Yeah. So this is what we've just proved. So this is going to come out, I hope, one day. Suppose G is a finite KP group, Q is a large subgroup, YL is not in Q. Yeah. Then what we can tell you is what the group is. So if P equals 2, you're looking at a Lie-type group in characteristic 2, or one of these sporadic examples. I mean, so here A9 and A10 are honorary sporadic groups for this thing, and omega 8 plus a 3 is, of course, sporadic, and and so on. So this is what pops out. And P is odd. Then it could be that P is 3, and we get a bunch of examples. These examples arise because of what Ellen was getting close to. The fact is that in characteristic 3, centralizers of involutions might have an SL23 in it. But then this SL23, say we're looking at, which one's a good case to look at? F4 of 2. Yeah, so the centralizer of an involution there, so the F4 of 2 is not, and P equals 3. So F4 of 2 for P equals 3, centralizer of an involution is an SL23, central product SL23, which is a Q8 central product Q8, but it's O2. And so we bump into examples. Yeah, good. Or we're looking again at this. This is the group generated by all the P local subgroups. That's a simple group of Lie-type and characteristic P of rank at least 3. And if we actually know G is of local characteristic P, we have a theorem that actually allows us to say that G is known, or F star of G is known. Or we could be looking at a weak BM pair. So this is where the monster case in P equals 13 comes up. And we can't say what the group is. We just get the local structure, because there are infinite groups around there that we can't rule out. And yeah. So that's the main theorem when Ym is not in Q. And in this case, there's some work on so-called symplectic amalgams that's applicable. And so this case looks quite easy. So we're very close to actually having a list of all the groups with a large subgroup. So let me just give you some clue as to how you might get to a theorem like this. It can only be a clue, of course. Yep. So let's take this as an example. So here is my, say, my subgroup M outside. Did I call it M? No, L. I called it L out. Here's my subgroup L outside. Here's the YL. It's Q to the 4. This Q to the 4 is not inside Y. Sorry, is not inside Q. But it is abelian. And it is normal in S. So Q normalizes it, and it normalizes Q. So I get Q commutate YL, commutate YL is contained in YL, commutate YL, which is 1. So I've immediately have quadratic action on my side in this case, right? So YL is acting quadratically on Q, and it's not in this group here. So let's begin more slowly. So first off, we know that Ym's not in Q, and we can look through the structure theorem, which tells us all about the Yms and all about the M's mod the centralizers of Yms, and we can pick some special cases out. So we find one such that M star mod the centralizer in M star of Ym star is an omega n or an sp2n. Now here, you say that doesn't look like an omega m to me, but of course it is. Right? This is O4 plus a Q. Yep. And it's acting on this module here as O4 plus of Q. So Ym here is the O4 plus of Q module, and these SL2Qs acting together as an O4 plus. And so that means we've just got to consider, well, that infinite number of cases, but it's more uniform than it might appear. Right? So remember, I could have chosen that parabolic initially, which is an SLN minus 3 cross SL3. And that's obviously not one of these unless I'm in the very special case that n minus 3 is 2. Yeah? So this is a restriction. It makes the investigations more quick. Just as I've said here, we have quadratic action right away. So there's immediate quadratic action. So it is possible that this ym is all I see. So what would happen if ym was just what I see? Well, the OP isn't, there's no more OP. Well, that would mean that I was actually looking at something like I'd be looking at SL4 in this case. Yeah. And that case has to be dealt with separately. Yeah. So if ym is OP of m star, we determine the isomorphism type of this, or we're in some very strange cases. Yeah, because ym is a normal subgroup of S. Yeah? And Q is in S. Yeah, so S normalizes everything in sight. Yeah, that's why you like this parabolic characteristic P thing. Yeah, so if you weren't in parabolic characteristic P, you'd be right. You'd have to scramble a little bit. Yeah. So if OP of M is bigger than M star, that's this case, yeah? So what do I see then? Well, if I look at the chief factors that this SL2Q has on this OP, I see it centralizes this bunch of triangle stuff here. Yeah? And it introduces just two-dimensional modules here. And this one here centralizes them. And this one induces SL2 modules there. So these modules for SL2Q cross SL2Q, they're not the same as this one. I have to have two different sorts of modules. Yeah? And so we show a subgroup nearly as big as Q acts quadratically. Remember, we're doing this in a generic case. Yeah? Right, and then that's not very well written. So this Q, it acts quadratically on this. Now, how does it sit? Let's just have a look at it. It sits as a CeLO P subgroup here and a CeLO P subgroup here. It acts quadratically on that piece, quadratically on this piece, but not on ym star. And that's the point. There's different modules involved. So, for instance, if we're in these big cases here, we find that we've got a natural module at the bottom. The other ones have to be spin modules. Right, so we take the normal closure L star to be the normal closure of ym in NGQ. So I've got ym is sticking above Q. I can take its normal closure. It's going to pick me up a group, picks me up a component. Yep. And it has quadratic action, and that gives me the structure of L mod Q. And then we state H equal F star of this gadget, and we prove that that's got a weak BM pair. So a weak BM pair or corresponds to a building. That's a rough outline of the proof. If P equals 2 or G has local characteristic P, we can show G equals H. Okay, so I'm more or less just drawing you this picture a little better. So that's what we start with, not knowing anything about OP of M. So there's a bit more detail of this case. We have ym star Q mod Q. It's just a group of order Q. Q comma ym star is this group here, this P cubed. Q cubed. And so we get Q mod the center of Q is a 2F module in that case. We know about 2F modules. That's the point. We know about module actions. Yep. So that gives us these two. So at that stage we have this parabolic and these pieces, and it allows us to put all the thing together, and we get HSPS ln plus 2 of p to the a. Okay, I'm done. A bit early. Sorry about that. Don't think anybody minds.
Thank you very much. Do we have any questions? Yes.
This looks like magic somehow. Because, I mean, you're using the structure of 2F modules and things like that.
Yeah.
You said, well, you have this assumption on the K group assumption, but is that enough to be sure that there is no other group acting? Because you only look at groups acting which come from local subgroups.
That's right. So we only have to look at, so not quite sure where your question is. So,
my question is whether this is all solid in a sense.
So when
it looks like magic,
so when you're in a free local subgroup, by assumption, we know the composition factors. Okay, and so long as I stay in that local subgroup, I can determine module actions and get the structure of parts of the group. Okay. I trade one piece off against the other.
Okay. So you only act with P local subgroups.
We never leave P.
Okay.
Yeah, so we stay at that, and then at some stage we get enough information to build a building, and we use the characterization of buildings. Yeah, so at a certain stage there's a geometric object on which this group is acting, and so it embeds into a group that you know.
So how far are you now from the classification of the final groups?
Oh, a long way, I think.
How does it embed somehow in a third generation group?
That's a better, more precise. That's a better question. Excuse me. So if your group is a characteristic 2 type, this replaces that. So it will give us a characterization of groups of characteristic 2 type. Now, whether anybody ever cares about the result as far as P odd is concerned is a separate issue. But actually, it's no harder to do P odd at the same time as P equals 2. So it will replace some part if people wanted to do that. I think it's more interesting just to see how the proof becomes uniform over all the primes somehow, so that you see that that you begin to get an understanding of groups of local characteristic P and characteristic P.
So you still have to worry about groups which are not local characteristic P.
That's right. So
no prime P.
Yeah. So that would be the way. If you wanted to apply this in its full strength, take a group that has no characteristic.